All right, today we're going to talk about an intuitive idea as to what limits are. So let's talk about limits and why do we care about them and sort of the idea as to how you would look at them. Although we're not going to compute any at the moment, we're just going to look at an idea. So let's start first with, let's say you have a graph of a function that represents, very straight line by the way, that represents the movement or the distance of an object to the origin or to a set point, let's say, with respect to the time. So let's say we go like so. And this is going to be the distance. So let's say you have here at a time A, let's say, the distance from the object to the initial point will be roughly, say, d1 or dA, why not? D sub A. And then at a time B, you would have it to be whatever this distance would be. Let's call it dB. Okay, so then what we know is that in this period of time that you could call delta t, that would be b minus a, so whatever that amount of time, you moved from dB to dA, so the distance that you covered was dB minus dA. So if you were to compute then the average rate of change, which is, if you remember, is going to be the delta D over delta T, in this particular case would be dB minus dA over B minus A. And this would give us, what this would mean, would be the average speed of the object in this interval. Now that should ring a bell because that's just going to be y1 minus y naught over x1 minus x naught if you were to do it in an xy plane, and that would represent the slope of the line that connects these 2 points right here. However, from my beautiful graphical representation, sure, you can see that the actual distance or the function that we're considering, it departs from that straight line, and that's not just because I'm terrible at drawing, but also because the 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 curve we drew is not a straight line. So that tells us that at certain points in our trip, say here, the average speed of this object is not the same, average rather, is not the same as the instantaneous speed. Just think about you're going on your car on the highway. There are times that you're passing somebody and you accelerate higher, close to the speed limit, and then you go below, right? As you make the pass. And so your speed is not always the same. So the instantaneous speed would be what you're looking on your dashboard, let's say. And then your average speed is from point A to point B, what was the distance you covered divided by that time, B minus A. So that is the difference between average and instantaneous. But to do an instantaneous speed, it seems like, or our intuition would tell us that this amount of time that we have to pass between our measurements would have to be really, really small. Actually, for it to be instantaneous, would have to be going to zero. But we cannot make it equal to zero because you would have a number divided by zero. And we don't know how to deal with that. So to make that division by zero, if you will, precise, we will need the idea of a limit. So instead of saying that delta t will be equal to zero, we will say that delta t will tend towards zero. Of course, this needs to be made precise. But the idea, since we're just doing an intuitive idea right now, is that we're going to let this delta t get close to 0. And algebraically, we'll have to make sense of what it means and what it represents for the function that we're evaluating. So that's going to be our goal. So let me show you one example where we will put a name to a function and we'll kind of draw it so we can have an idea as to what's going on. So let's grab here now an xy coordinate. Let's not do any t and d anymore. Let's go to xy coordinates. And let's say that our function will be the function y equals f of x, where f of x is given by, let's say x squared minus 4 divided by x plus 2. So remember what you did whenever you wanted to find vertical asymptotes. You would find when is the denominator equal to 0. You see, again, dividing by 0 seems to be the theme here. And in a lot of cases, and mostly when we're talking about later on derivatives, it will be the case that we're looking for zeros in the denominator. That will be somewhat useful. So anyways, we set the denominator equal to 0. Somewhat, actually, very useful. My bad. So we subtract 2 on both sides and we get x equals negative 2. So let's say 1, 2 boxes to the side and we put negative 2 here. And here at this line x equals negative 2, we would expect to have an asymptote. But if you remember from your pre-calculus class, you also wanted to check if that x equals negative 2 would make the numerator 0. So when you plug it in, you get negative 2 squared is 4 minus 4 is equal to 0. But that shouldn't be too much of a surprise because if you factor this here, you get that this is x plus 2 times x minus 2 divided by x plus 2. And you say, well, I have a x plus 2 in the numerator and x plus 2 in the denominator. Let's go ahead and cancel. And that's what we've done in the past. However, what happens when this is negative 2, this x? Well, that becomes 0 in the top and 0 in the bottom. 0 in the numerator, 0 in the denominator. So you get 0 divided by 0. So what is that equal to? We don't know. We have to make that precise. So if you're going to divide like that, we gotta be careful as to when is the factor we're canceling, when is it 0? So this is equal to to y equals x minus 2 if x is not equal to negative 2. Okay, so we have to make that caveat. So, however, that is actually quite important though, because that gives us a way to graph this function. We go to negative 2, that's our intercept. That is the equation of a line. So I go 1 to the right and 1 up, 1 to the right and 1 up, 1 to the right and 1 up, and now see me try to connect those dots. Wish me luck. So we're gonna connect the dots if I can see my pointer. Where did my pointer go? Here it is. Almost. Oh well, we'll leave it at that. However, let me scroll one bit because I want to focus on what happens here. So one down, this point here at x equals negative 2. You see, x equals negative 2 is not in the domain of my original function. So I have to exclude it from the graph. That's why I made this open hole here. And the graph would continue. Now, if you plug this in some software, say Desmos or Mathematica or whatever you use, the graph would be a line. They wouldn't even give you any consideration to that x equals negative 2. But we do know that that point is not in the domain, so we exclude it. So that is the graph of the function. But now let's see what's really happening. I cannot say that as x approaches, or as x is equal to -2, the function takes the value of -4, what would be the corresponding value here in the y-coordinate. Here in the y-coordinate, I have -4 for that point. I cannot say that the function takes the value. So f of -2, f being x squared minus 4 over x plus 2, this is not equal to -4. But we're gonna then make this the limit. So we're gonna say that in the limit sense, the limit as x goes to -2 of this function is going to be the y value, which is -4. So we will be able to make sense of that expression, even though we're not saying that the function takes that value at all. But we will make that a little bit more precise later on, and we'll do a lot of examples so this makes sense. But we'll leave it at that for this one video.